This is a short video about standing waves in air columns. You will come across two types of columns or pipes. Open, open, so it's open at both ends, or open, closed. Now, in both cases, you will get reflection from the ends of the pipes, even if it's open to the atmosphere. The discontinuity in the medium will cause reflection. So you will have waves traveling in one direction, reflected about the end and going in the opposite direction. And that is the situation that leads to standing waves. So the thing that you have to remember is that at the open ends of the pipes, this would be a pressure node, which means that the pressure is continuous there and it is the same as atmospheric pressure, so it's a node. But the displacement, the motion of the air molecules is a maximum there. You need lots of movement so that the sound can come out of the pipe into the atmosphere and you can hear it. And so this would be a displacement antinode. Okay, but when you have a closed pipe, like at this end, the molecules they crash into the wall, they can't go anywhere. That would be a displacement node, no motion. So that's a displacement node. And so the pictures that you draw for these standing wave patterns, you've got a choice. You can draw the pressure waves or you can draw the displacement waves. I like to draw the displacement waves. And so they look like this. For open, open, it's a displacement antinode at the end. So there's the fundamental frequency. So this is the fundamental, or if you like, you can call it the first harmonic. L is the length of the pipe. You can see that that's actually half a wave. And so the first wavelength is twice the length of the pipe. The fundamental frequency is the speed over the wavelengths. Now this is going to be the speed of sound in the pipe. And so that depends on the temperature of the air in there. But they'll tell you in the problem what that is. If it's 20 degrees Celsius, you're going to use 344 meters per second for that. And so this leads to the fundamental frequency being V over 2L. The next harmonic, you just keep adding nodes. So the first one has one node, one displacement node. The second one has two displacement nodes, and they just fill in the wave. And so the second harmonic, which is F2, is twice F1. And so it would be V over L. And this carries on so that you get the basic relationship is the nth harmonic is NV over 2L. Now that looks exactly like the string, and it is exactly like the string. You have integer harmonics. Every one is an integer of the fundamental. And you have 2 times L, where it's the length of the pipe. The only difference is you're using speed of sound now, not the speed of the waves on a string. Now with an open closed pipe, it's a little bit different. Because you have one end an antinode and the other a node, the fundamental, the longest possible wavelength you can get looks like that. So here's the node, and here's the antinode. And you can see that that's only a quarter of a wave. And so the fundamental frequency here is V over 4 times L, because the first wavelength is 4 times the length of the pipe. In other words, length of the pipe's a quarter of a wave. Now, when you do the next picture, you add a node, you now get a picture that looks like this, which is 2/3 of a wave. And so there is no second harmonic. This is the third harmonic, and it's 3F1. So this is third harmonic, and there is no second harmonic. All the harmonics are now odd. And so you can see that that's 3/4, sorry, it's 3/4 of a wave, not 2/3, 3/4. There's a quarter here to here, and then here to here's another quarter, and then here to here's another quarter. So it's 3/4. And so the wavelength, you need 4/3 of L to fit a full wave in. Okay, and then the next picture, it's the 5th harmonic. So you add another node, 1, 2, 3, join them up. And this would be the 5th and the 7th and so on. And there is no 2, 4, 6. Okay, and so F5, it's still 5F1. But the wavelength here, lambda 5, is now 4/5 of L, because there's 5/4 of a wave inside L. And so the formula here is Fn is Nv over 4 times L, and N is only odd, 1, 3, 5, 7. Okay, so those are the formulae that you need for working out the harmonics in open closed pipes and open pipes.